So now we're back to learning GDScript from zero, and this is an open source project by GDQuest.com. All right, so let's continue where we left off over here at time delta. So we've seen how we can use our character's process function to make it move continuously. True. There it goes. Anyway, there we go. But it's not just our character that needs a process function. Almost everything in the game has a process function. All right. Dozens of times per second, Godot runs every process function in the game to update the game world. Okay. After that, it displays an image of the game world on the screen, and we call that image a frame. Yes, that's how that works. Godot then moves on to calculating the next frame. Yes. And this happens dozens of times per second. Okay, let me back up. As this happens dozens of times per second, we get the illusion of movement. It's similar to how traditional animation works. Yes, and I mean that's how it is. Like even like look at the mouse pointer. Like those are like frames per second. Like whatever I have the frames per second set at, that's why there's like this disjunction. You can see there's definitely space in between the images of the pointer as they're being displayed across the screen. You know what I'm saying? It's not like this isn't like some sort of trick with our eyes to where we can't what's the word, to where we can't detect it or something, like helicopter blades or something. No, this is actually just that's how many frames it is. That, you know, every single one of those little after shadows or whatever you call it in whatever, every single one of them is just a frame, right? And we're seeing the frames go by. Anyway, whatever. Let's keep going. I'm not an expert. Let's go. We may have heard of frames per second. True. Or FPS for short. Yes. Games often run at 60 frames per second. True. It means that everything in the game updates 60 times each second. The number varies while playing, depending on the game and the device it runs on. On powerful computers, we may get frame rates in the hundreds or thousands of frames per second. True. So let's look at the process function in more detail. What parameter does the process function take? Right here, we've got func process delta rotate 0.05. So it's going to be the delta right here. So we've got that right there and submit it. All right. So we're right. The process function has one parameter named delta. All right. So frames take varying amounts of time to calculate. Depending on the game, the computer, and what the game engine needs to calculate, frames take more or less time to display. True. There will always be milliseconds variations from frame to frame. Okay. That is why the process function receives a delta parameter. Okay. Delta represents a time difference. It's the time passed since the previous frame in seconds. All right. So like, let's say this, between any two of these, the time between making the first one and the second one, that's the delta, the split nanosecond, whatever. What do we call them? Millisecond. Anyway, so yeah, let's keep going. We can use it to ensure that the changes between frames don't make the game's behavior unreliable. Okay. This is because different computers run differently. So a fast computer will have more frames per second than a slow computer. Yes. If we ignore delta, the game experience will vary depending on the computer. Delta helps make game experiences, consistent for everyone. What do we know about delta? And then let's select all that applies. It's a value in seconds. Yeah, well, milliseconds, but still. It's the time it took Godot to complete the previous frame. Yes. It varies each frame. Also, yes. Submit it. There we go. All right. So we're right. Delta is the time it took Godot to complete the previous frame in seconds. It's very small because frames happen many times a second. It varies each frame because Godot needs to process more or less each frame. Yes. So there's more or less going on in the thing. I mean, you can just press Control-Alt-Delete and look at the taskbar and see the fluctuations of the CPU, and you can know it right there. But anyway, let's keep going. Multiplying by delta. So the delta we get in process is a time difference in seconds. It will generally be a tiny decimal number. To apply delta, we need to multiply our speed values by it, all right? And this is the part I'm having a little trouble with because the logic, I mean, I see it clearly, it's the logic, but I just don't get it. To apply delta, we need to multiply our speed values by it. So we got func process delta, rotate 3.0 times delta. So instead of like 0.05, we do 3.0. Let's set it to true. And there it goes around and around. And so this is the variable that we would change to get this thing to slow down or speed up. All right. Because delta is going to be delta whatever, no matter what. So when multiplying by delta, we make motion time dependent rather than frame dependent. That's essential to make our game consistent and fair. So why do we use the number 3.0 in this example? Yes, why? Okay. I'm still having trouble grasping this. This is some serious logic that you got to use to make this work. But it works. I mean, you can see it work. You know what I'm saying? So let's go. At the top of the lesson, we made the robot rotate a fixed amount every frame, 0.05 radians. True. In the example above, we now multiply the argument by the very small delta value, a value way below 1, of course. It makes the robot turn at a constant speed over time. However, multiplying by a number below 1, like delta, makes the result smaller. True. I mean, smaller than 3. Or smaller than whatever the multiplier is. Yeah, true. To compensate for that and make the robot turn fast enough, we use a larger number than before, 3.0 instead of 0.05. True. Those numbers have two different units. 0.05 is an angle in radian, yes, while 3.0 is an angular speed in radians per second. True. But when you multiply it by delta, which is frames per second, you take this. What is it? What is it? That's the thing. I mean, this is some math. You know what I'm saying? And I'm just trying to say, how do you get radians out of this? Because clearly, when you go from 3.0 times delta, you're going to get a radian. Hey, what's up? Hey, I'm back. I'm here. Yeah, I'm editing this. All right, so I got it. While I was right at that second, right at that point, right there, wherever this is, 8:09 of editing it, of whatever, reviewing it. I understand now. Look. Okay. We got this open. What did it say? Hold on. I'll put this over here. Let me make this bigger. Let me bring this to the front. Let's see. Let me bring this to the front. All right, there we go. And what did it say? What did it say? Okay, so we're okay. Look, so this thing. Where was it? Oh man, it's not even there. I gotta write that too. Okay, so like rotate, all right? Well, let me get this out. Rotates like this. Okay? Rotate. Look at this. Rotate is like radians, okay? It's expecting radians. Oh man. Okay. It's expecting radians in the rotate, right? Okay. So delta, this is the symbol for delta, equals radians rads per second. All right. And then so we're saying delta times, what was it? Delta is seconds. No, delta isn't radians per second. Delta is seconds. And the angular speed is radians per second. So delta is seconds. Delta equals, where's the, I just do this here. Delta equals seconds. Seconds. Sec. Okay, that's good enough. And then the other number is radian. What was it again? Angular speed. Angular speed. I'm just making that up, honestly, because I don't know how to do that. Is, and let's make these arrows. Angular speed is rad per second. Rad per second. So when we multiply delta times rad speed, it's the same as seconds times rad seconds. And we know from math, these cancel each other out, and it just ends up with radians. So that's where this stupid crap is. That's the math behind it. And I didn't realize that until just then. Yeah, it totally makes perfect sense. Yeah, we're canceling out the seconds because the delta is the seconds and the speed is the rads per second, and we're just going to be left with radians. All right. And so thus the rotate is now in radians, and boom, we've got a program. All right. So hopefully that makes sense to you guys if you remember your little algebra. No. And there's that. So let's get back to recording. I'm going to get back to editing. You get back to watching. The thing only runs using radians, right? So, man, I kind of want to get out a piece of paper and like do some math, do some like algebra on it to make sense of this algebraically. But I don't have one of those things. I mean, the best I got is paint, and we're not going to do that. Then we multiply the speed by a time delta, and it gives us an angle. Don't worry if it's a little confusing for now. It'll eventually click as we deal with speed, acceleration, and motion in our game projects. The main thing for me, because this logic, I mean, I know it's there because I've seen it, right? This is I always do. Well, at least for this one, I'm doing rehearsals for each one of these videos. I've seen it work, and I saw something in ChatGPT explain why when we do this, it'll give a slow computer. It'll make a slow computer go at 60 frames per second. It'll make a fast computer go at 60 frames per second because of the logic. But geez, I forgot. I really I'm having a hard time figuring out how it works. Whatever. Why the time between frames matters. The time it takes to display a new frame varies. True. If we don't take that time into account in our code, our game will have gameplay issues and bugs. Also true. Godot provides that time to the process function through the delta parameter. True. In the example below, the top robot moves using delta. As a result, it moves at a fixed speed. The bottom robot moves over a constant distance every time without taking delta into account. It will move faster or slower than the top robot on our computer. The bottom robot will move differently for everyone, but that's the thing. We can't tell because we're only on one computer. Maybe if I could put a phone here. So if we play it, yeah. So, I mean, there's really no way to tell. I mean, I can't just make my computer go like super slow, like right off the bat. You know what I'm saying? Whatever. Anyway, if you look at the math, if you type this delta thing down in like ChatGPT, it'll give you the math. It'll give you the math about it. But I still don't get it. But whatever. Multiplying time-sensitive values by delta makes them time-dependent rather than frame-dependent. True. Thanks to that, we get reliable movement over time. Without delta, frames vary from computer to computer during gameplay. Because of that, the movement will differ for every player, making the game inconsistent and messy. Yeah. So yeah, just this delta thing, if we for a mathematical reason that I've witnessed with my eyes, and still don't understand, but I saw the math happen. I understood that math happened. This makes sense. Okay. No matter what computer you're on, if you do rotational speed by delta or whatever, something by delta, it'll average out as the same, whatever. You'll get the same result on every computer, no matter what. That's the point of it. It's so whatever. Anyway, let's go. So so what's this? Rotational speed times delta. We're subtracting data from rotation. No, we're not. We're adding, we're dividing, we're multiplying. Yeah, it's times. Anyway, if you don't know yet, this is the times button. This is multiplication right there. Submit it. There we go. The star symbol means we're multiplying rotational speed by delta time. True. So in the next practice, we're going to use delta to make rotating time dependent. Like I'm telling you, when I was rehearsing this and I got to this point, and this is all they gave us, I was just staring at this for like 5 minutes, just going, what did I just read? And then I went to ChatGPT and it did it again. It said pretty much the same thing. And I was just like, what did I just read? And that's why I'm telling you guys right now. You got to look it up yourself if you don't get it, because I don't even know. Okay. I just know that it works. I know it works. I've seen it. I've seen them try to explain it, and it just works. My mind can't I can't wrap my head around it. Kind of like recursion. Rotating unit delta, using delta, I say. Practice. Let's go. So rotating using delta. At the moment, the rotation of the robot is frame dependent. True. We're going to add delta to make the rotational speed time dependent. The robot should the robot should rotate 2 radians per second. Okay. So rotate 2 times delta. I mean, I'm just doing this because, you know, that's what we were doing. But, you know, I know this will work. Now, why? I don't know. All right, I'm back one more time. So yeah, just listening to that. What did I just say? Hold on. Let me put on my headphones again. I just said, I don't know. Oh yeah. I remember. So the thing about that is a lesson I need you to, I would like to convey. Okay. That's all I can do. It's my video, right? The thing I would like to convey, that's not even a lesson. The thing I would like to convey is that on the previous time I cut in, when I did that little math thing on the paint, when I did that, I was on my 3rd time reviewing it. Okay. So the first time I did a rehearsal, right? Okay. And then the second time I recorded the thing. And then the 3rd time of going through it, I was watching myself go through this thing, right? And it finally clicked, right? So I'm sure you remember from school and stuff, where sometimes people would say, yeah, you got to do in college, you got to do like 1 hour for every hour of class, you got to do like 2 hours worth of studying, or you won't get it, right? So 1 hour, 2 hours, and 3. So that's 3 hours. So that's basically for every chapter you read, you got to read it 3 times, right? Or in my case, I do the thing twice and then I watch it. And so 3 times, just like that. So that's one thing I'm doing that I can't show that I'm doing that on the video, because how could I? Anyway, that being said, so yeah, I'm going over all of these 3 times. And so that thing that I had no idea about, like that, like a snap finger. Anyway, let's get back to it. All right. Moving in a circle using delta. In this practice, we're going to make the robot move in a smooth circle using delta. To get this movement, the robot should rotate 2 radians per second and move 100 pixels per second towards clockwise. All right. Note, we're going to write the values in the parentheses when calling the functions. If we define extra variables, we will not be able to check our practice. Okay. Let's do it. Okay, so we got these methods down here. So let's start with rotate. So rotate. What did you want? 100 pixels per second? 2 radians per second. Rotate, so we'll say delta times 2. All right, and then we'll do the move 100 pixels per second. So we'll use whatever the second one was. Move pixel, what was it? Move local X, of course. So move local X. Now, oh no. And then so the parameters we have are delta scaled Boolean. What? Float. Delta. Is delta the okay, well it's the first parameter, so we got to do that. So let's just say 100. Delta means distance, right? Anyway, does it mean something? It means, I think it's the difference between 2 different numbers, I guess. I forgot. Let's go. Let's see if this works. He's flying. He's flying. He is flying. He's not moving in no circle though. Okay, what? What? I could have sworn I did this. All right, rotate delta times 2. Is it 2 times delta? Move local X 100 times delta? No, that ain't right. Is that it? I mean, there it is. I mean, proof's in the pudding, but... So we got to multiply delta on every single one, it seems. Okay. Okay. All right, so we learned that. Okay. What? We're just gonna do that. Nah, we gotta do. I gotta make a 5-second freaking video for this one. Maybe not. We'll see. Anyway, maybe there's gonna be 1,000 lines after this. Who knows? Anyway, so now we're on to using variables to make code easier to read, and we'll see you next time.